And now, we will begin our study of thermodynamics. In our textbook, this is chapter 19. We are going to be skipping chapter 18. Thermodynamics really covers the intertwining nature of energy and matter in chemical reactions. In kinetics, we looked at how quickly reactions progress, right? Or rather progress. How fast things are happening, how quickly we're producing our products. In the 3 equilibrium chapters, we looked at to what extent does the reaction take place? How much product do we make? How much reactant is left over? What happens when we do things to that equilibrium? And now we're going to be looking at how energy plays into how that extent of reaction happens. Thermodynamics will tell us nothing about rate. Rate is solely the domain of kinetics. So this chapter we're looking at energetics and how they dictate how far a reaction will go. And this chapter is very much conceptual. There is math in this for sure, but the math required is a lot easier than the math we've seen for the equilibrium and kinetics chapters. But on the other hand, we do have more complex concepts. So this chapter is fairly wordy in the text. There are a lot of words to explain what's going on. I'm going to try and do my best to pick out the parts that are important for you to learn. And I'm not going to go into too much detail as to the background of them. If you are interested, the book does a good job of explaining them, except it is particularly complex. It may take several reads to go through. So, thermodynamics then. What we're really looking at is spontaneity. And that is, will a reaction take place or not? Will this reaction, if I put my hydrogen and nitrogen together, will they combine to form ammonia? That's the idea of spontaneity. We're going to see that spontaneous processes will happen without outside interference. But really this answers, will a process happen? And we have 3 answers to this question. Will a process happen? We have yes, no, or at certain temperatures. So with this question, we're assuming no outside interference. So without hooking things up to a battery and supplying them with a ton of electrical energy, we're really just looking at a system by itself. Will it happen or not? And we can consider several things. For example, will water evaporate? Oh, no, that's going to be the third one. Will hydrogen and nitrogen react together to form ammonia spontaneously by themselves? Yes, they will. And this is something we'll look on how we know this later on. So that's great. We know that. Another one would be, will salt break into sodium and chlorine? No, that is not something that is going to happen by itself. If we want sodium chloride to break apart into sodium metal and chlorine gas, we have to do a lot of things to get that to happen. It will not happen by itself. So that is a non-spontaneous process. The combination of hydrogen and nitrogen is spontaneous. That will happen without us interfering. And then finally, the one that's probably the most common is the at certain temperatures answer. And so we have to ask ourselves, will this water evaporate? Yes, it will at certain temperatures. Will this water freeze? Yes, at certain temperatures. No, at other temperatures. And so we'll investigate in this chapter why we get these 3 answers. So, of course, if you take an ice cube, put it out on your desk, if your desk is at the temperature below 0 degrees Celsius, your ice will not spontaneously melt. Again, unless you add some outside heat or something. At 1 degree Celsius, it will spontaneously melt. So we will see that some processes, most processes, will happen only at certain temperatures. And that's really the question we're answering throughout this chapter. And so the first thing we need to look at is the idea of reversible and irreversible processes. So reversible processes and irreversible processes. Irreversible processes. In short, reversible processes involve infinitesimal change to systems. Meaning, if we're looking at something like heat transfer, so normally, coffee, hot, loses heat to the surroundings, which are cold, and that doesn't go backwards. The surroundings does not decide to say, okay, now I'm going to heat your coffee up for you, right? Doesn't really work that way. Heat flows from hot to cold. However, if we were to somehow do this infinitesimally, with the temperature changes being infinitesimally small as the heat is transferred, it would be reversible. Because we can say, okay, as soon as like one phonon, one unit of heat, leaves my coffee into the surrounding air, there's a chance that phonon could come back to the coffee. However, over time, if we're looking at it rapidly, like in real life, that doesn't happen. But if we, say one phonon leaves the coffee every 1 hour, we can consider it overall reversible. Or if we're talking about volume changes, if we are increasing the volume of a cylinder or something infinitesimally small, it's technically a reversible process. There's no energy lost if we do that. However, that's not real life. We do not see reversible processes in real life. We're going to see that all real processes, things that happen in real life, are technically irreversible. And we don't mean that you can't go backwards. It just means that there's some energy change associated with it. So you can take your water and freeze it again if it's melted, but you have to cool it down then. You have to take some energy away. So there's going to be energy transfer associated with that. And so it's technically irreversible because we had to do something to take the energy away, right? So in order to reverse things, we have to apply energy in some way or another. And we're going to see that those all real processes will be irreversible. And we'll see why that's important when we bring in the next topic, which is entropy. So I realize we have not written a lot yet, but again, a lot of this will be words because many of these concepts are not easily conveyed mathematically without doing very advanced math. However, we will do simple math towards the end of the chapter.